What we're going to do now is take a look a little bit more at Euler tours and Euler trails. So first of all, remember that a trail is a walk in a graph where no edge is repeated. And an Euler trail is a trail that covers every edge of the graph, but it doesn't necessarily have to start and end in the same place. Whereas if it is a closed Euler trail, which means that it does start where in the same vertex that it ends, then that's called an Euler tour. So just keep that in mind, that an Euler tour is a closed Euler trail. And if the graph has such an Euler tour, then it's called Eulerian. And we saw in a previous video that a connected graph is Eulerian if and only if every vertex has even degree. And we went through the proof of it, but I just want to give a brief reminder for how the proof works. So first thing to keep in mind is that if the graph is in fact Eulerian, it should be pretty clear to see that it will have to have every vertex having even degree. And the reason is because if you're to take a look at any particular vertex of the graph, and you know that there is an Euler tour, every time the Euler tour uses up the vertex v, it'll have to enter through one edge and exit through a different edge. And every edge in the graph gets used up in the Euler tour, and this happens for all the vertices. So if you use up the vertex some number of times, like k times, in the Euler tour, then that will mean that the degree of the vertex will have to be equal to 2 times k. And not only that, the place where you start and end, so let's say you have some vertex u and your Euler tour goes all the way through all the edges of the graph and then ends up again at u. Now it may have used u somewhere inside of here as well, but because it also starts and ends at the vertex u, and then every other time it must have been used was also used twice, we again know that it has an even degree. So this part is fairly straightforward, that if it's Eulerian, then every vertex has even degree. The part that's a little bit more difficult to see is if every vertex has even degree, then it's Eulerian. But what we can do is we can take a longest trail, so this is in this direction, so we have all even degree. And the basic idea is to take a longest trail, so we take a longest trail w, and if you take a look at this trail where it starts at some vertex and it goes along, it might repeat vertices, but it cannot repeat edges, and it ends somewhere, say vertex VL. Now what we do is we take a look at this longest trail, and we observe that if in fact there is another edge that is incident with this vertex VL, then we could simply extend the trail. So if there is a vertex like this somewhere out here adjacent to VL, then we can extend to a longer trail. So that cannot be the case. We know that cannot be the case, otherwise we could extend the trail and we've already got a longest trail. Well, we've already used up then all of the edges that are incident with this particular vertex VL. So if we think carefully about vertex VL, I'll just draw it over here, maybe it was used several times in this walk. Maybe it was used and we had to enter it through the walk, and then we had to exit, and maybe we entered it again and had to exit. And then at this point right here, when we enter into VL again, we enter like this, and we cannot exit again. The only way that this would resolve itself is if VL is in fact the start and the end of this trail. And the reason for that is because we cannot have a picture like this. We know that the degree of VL is even. So we know that we cannot just end at VL having an odd degree like this. So we now know that VL is actually the same as V0, that these are actually the same vertex, and W is closed. So now we have this longest trail W, which happens to be closed, and what we really want is to show that this trail W is an Euler tour. We already have shown that it's closed, but we need to now show that it covers all of the edges. So if it's not an Euler tour, if W is not an Euler tour, Well, what does that mean? It means that it missed some of the edges of the is that not all edges got covered by W. So now I argue that because of this, there will be an edge which is somehow adjacent to the walk W, the trail W. So it would look something like this. There's a vertex that is on the trail, and then there's an edge which is not contained in the walk. And the reason why I know such an edge exists is because, first of all, not all the edges of the graph are covered, and if there was an edge out here which was not covered, then there's these two vertices which don't belong at all to the trail. However, because there is definitely a path that connects this particular vertex right here to any vertex of the trail, and that's because the graph is connected, I know that somehow I'll be able to get from this vertex to a vertex on the trail, and therefore the last there will be an edge like this which connects me to the trail. Now it's also possible that I have some sort of edge like this where both end vertices belong to the trail. So I don't really need to worry about this case over here, so I'll just go ahead and erase it. If that case occurs, then it will reduce to one of these two pictures. So basically now we have this extra edge, and I'm going to call this extra edge F. So this edge right here, I'm going to call F. And similarly, this could be the edge F. Doesn't matter which one. So now I claim that we can get a longer trail. We can make a longer trail, and here's how. I'll just trace it out in green for you. Let's say this is the type of F we have. Well, what you do is you start with the edge F, and then you work all the way through the trail W, which these two vertices are identified, and then you keep going all the way through and back to where just before the edge F. So now this contains all of the edges of the trail W, and it also includes the edge F. So it's basically F together union with this trail W. And that's going to be a longer trail, which is a contradiction. And we should remember that the reason it's a contradiction is because we took W to be the longest trail. Now, what you might be worried about what happens if in fact this was the edge F, but there's no need to be worried. If the F up here was the edge, you can simply take this edge, trace again all the way through the walk until you get to the very end, and keep using these edges over here. So you pass through that vertex and keep using these, and then you end here. And similarly, it will have the same number of edges that the walk W had, as well as the edge F. So in either way, this longer trail will have the number of edges in W plus 1 edges. So it's longer, and that's the contradiction. So that's the basic rundown of how that proof went. And so just try to keep in mind that a graph is Eulerian if and only if every vertex has even degree. Something you might be wondering about now is, well, when does a graph have an Euler trail? So not necessarily an Euler tour. And you also may recall that from the bridges of Königsberg, we were looking for Euler trails. So we're going to go ahead and take a look at that now. And we saw in the bridges of Königsberg problem, actually, we had the answer. So this is our new theorem, that a connected graph, has an Euler trail if and only if it has at most 2 vertices of odd degree. And I believe the way that I phrased this in the video on the bridges of Königsberg was to say that it has exactly 0 or exactly 2 vertices of odd degree. And I want to point out right away that this is the same statement, because keep in mind that a graph has an even number of odd degree vertices. And you can review this in the video that talks about how the sum of the degrees of the vertices in a graph is equal to twice the number of edges. This was something that came straight from that proof. So because we know there's an even number of odd degree vertices, this is the same as saying there will be either 0 vertices of odd degree or 2 vertices of odd degree. So the proof of this basically follows because we've already done the harder proof above. So the proof of this in the first direction should be very straightforward. We can go ahead and say if G has an Euler trail, then it'll be a trail that uses up all of the edges, and it maybe starts at U and ends at V. Then, as in the proof of the above theorem, and I don't mean this theorem, I mean the previous theorem. So as in the proof of the previous theorem, we know that all of the vertices except possibly the end vertices, in fact the end vertices are the problems, so as in this proof, all vertices V that are not all vertices W, I should say, W that are not one of these end vertices has even degree. And that should make perfect sense because it's the same as the beginning part of the previous theorem, where you take a look through your Euler trail, and for any intermediate vertex, not the end vertices, you can make the argument that it'll have even degree. So in particular, it's possible that these ones have even degree, U and V, but they might not. And so if they have odd degree, they are the exact 2 that have odd degree. So we have either 0 or 2 vertices of odd degree. We have either 0 or 2 vertices of odd degree, right? Because either these guys have odd degree, in which we have 2 of odd degree, or they both do not have odd degree. And that's because of this counting argument up here that says we must have an even number of vertices which have odd degree. Okay, so now what about the other part of the proof? The part that says if there are at most 2 vertices with odd degree, can we show that there is an Euler trail? So let's go that way. So let's suppose that there are at most 2 vertices with odd degree. And now we have 2 possible cases. If there are no vertices, if no vertices have odd degree, then we know by the previous theorem that there is in fact an Euler tour. We know that it's Eulerian. Then there is an Euler tour. So in particular, an Euler tour is even better than an Euler trail. It's an Euler trail which is close. So we're done. And if there are 2 vertices of odd degree, here's what we do. We're going to let U and V have odd degree in the graph. And now what we do is we simply add a new vertex. So here's U and here's V in our graph G. So we have some connected graph G. And now we're just going to modify this graph by adding a new vertex W. So add new vertex W and new edges UW and UV. So in the old graph, these guys had odd degree, so some odd number of edges here and some odd number of edges here. And now what we've done in the new graph is we've added in this vertex, this vertex W, adjacent to U and adjacent to V. Well, what did we just do? This guy now has degree 2, and now we know that the degree of U is even, and so is the degree of V. These are now even, because they used to be odd and we simply added an edge. So let's talk about this new graph. I'll just highlight it in pink here. So this new graph is everything the old graph was, as well as this new vertex and new edge, and I'm going to call that H. So the new graph H that results has all vertices having even degree. All vertices of even degree. Right? Because U and V were the only two that were odd. Any other vertex out here in the graph before had an even degree. Well, we already had the theorem which we saw earlier in this video that if all the vertices of a connected graph have even degree, then that graph will have an Euler tour. So we know that H has an Euler tour. Alright, so there is some Euler tour throughout this graph, and we can choose to start and end the Euler tour at W, because remember, an Euler tour is closed, so it goes around and it ends up where it started. But you may as well just say that if you want it to end and start here, it could also end and start here, or it could end and start here. It doesn't matter where you say the end and the start is once you have a closed trail. So in this Euler tour, we can take the Euler tour to start at W and then end at W. Alright, well that means that it's going to have to go somehow starting at W, using up this edge, going through the rest of the graph somehow, coming back, and then using this edge to get back to W. So what we can do is we can take the piece of this Euler tour, so the portion of the Euler tour with W removed, and thus the edges UW and UW and VW. That's right, that should have been up here, this correction. This should have been VW is what I meant to say. That's what I drew up here. So those edges and that vertex removed, that portion of the Euler tour is an Euler trail from U to V. So we've just found the Euler trail. And that's what we were trying to do. We said that if there are exactly 0 or exactly 2 vertices of odd degree, find an Euler trail. With 0 vertices of odd degree, it's easy. We just use our previous theorem. And if there's 2 vertices of odd degree, you can make this argument by tacking on a new vertex with these 2 edges incident, and then finding an Euler tour in the new graph, which then results in an Euler trail of the old graph. So that completes the proof, and we now can see that Euler tours exist if and only if every vertex has an even degree, and we also know that Euler trails exist if and only if either every vertex has even degree or exactly 2 of them have odd degree.